All right, welcome back, everybody. Welcome to chapter four. We're going to change gears quite a bit here when we're going into chapter four. Going to leave polynomials behind for a little bit. Going to talk about some brand new types of functions, exponential functions, logarithmic functions, talk about rational powers, all sorts of cool stuff. All right, let me get the slides up and let's get going. There we go. Okay, so this is the first section. It's all about fractional exponents and radicals. This chapter is actually quite a bit shorter. Chapter three is a long chapter just because there's so much to cover. I mean, polynomials is a huge, just huge thing. You got to talk about lines, you got to talk about quadratics, you got to talk about polynomials in general, and then you got to talk about how they compare to rational functions, all that kind of stuff. Here, this chapter is much shorter. So the chapter is titled Exponential and Logarithmic Functions because that's our main goal. But our first section, the one we're going to do today, is all about fractional exponents and radicals. So we're basically going to extend our understanding of exponents to rational exponents, exponents that are rational numbers, and maybe even irrational numbers. Section 4.2 is where we'll talk about exponential functions. These are really important functions in math and science. Logarithmic functions, which are really just the inverses of exponential functions. There's an inverse relationship there. And then the last section is properties of logarithms, kind of motivating why we like logarithms. They make certain things easier to work with. So it's good to look at their properties. But let's focus on what we're going to talk about today. So this section, we're going to review our fundamental intuition of exponentiation. We're going to get a motivating question to motivate what we're going to talk about today. We'll talk about rational exponents, properties of exponents again, and then a really important technique here, factoring expressions with fractional exponents. Then we're going to talk very briefly about irrational exponents and the notion of continuous exponentiation. Then we're going to talk about radicals. Those are those little radical symbols, right? We're going to connect radicals to rational exponents. Then we're going to go over some properties of radicals that we've encountered a little bit in the previous chapters. But now we're gonna formalize them a little bit more, and then we're gonna finish up talking about how to rationalize parts of an expression. Okay, so quick review. If you remember from back in chapter one, section one, you can think of exponentiation as repeated multiplication. Okay, and that we denote it with a superscript like so. So whenever you see a superscript, you can picture the exponents. I'm sorry, the number the exponent is attached to being multiplied that many times, right? So b to the n is like b times b times b that many times. So for example, 2 to the sixth is multiplying 2 six times, you get 64. 7 cubed, multiply 7 three times, you get 343. Is that right? Yeah, 343? Probably right. Um, the result of an exponentiation is called a power. And this was one of the things we talked about way back in chapter one. You can kind of think of an exponent as counting factors of the base, all right? It's basically telling you like how many times you're going to perform the multiplication in an intuitive way, if you want to think about it intuitively. So 2 to the sixth means you've got six factors of 2. This is telling you how many factors of 2 there are. X to the fifth means you've got five factors of x. You could think of 3 to the x as having x factors of 3. And that's where things get a little bit, well, the intuition can help you, but the rigor disappears a little bit. So the question we're going to kind of answer today is, hey, what if x was 1/2? What does it mean to say, like, I have 1/2 of a factor of 3? And we're going to make meaning of that in just a minute here. Square root of 3 squared means you got two factors of square root of 3. And so that leads us to this motivating question. How could we extend our intuition of exponents as counting factors to rational exponents, exponents that are rational numbers like 1/3, 3/4, 137 over 45, etc. So we're just going to kind of motivate that intuition and see how it can really help us work with these expressions easily. So if an exponent is counting factors, then an exponent like 1/2 would indicate that you have half of a factor of that base. So let's just let x be non-negative for now. We won't worry about negative bases right now. Then x to the 1/2 would indicate that you have half a factor of x. So that might feel weird at first, But consider this, if you've got half a factor of x, and then you multiply it by another half factor of x, then you would have two halves of a factor of x. In other words, you would have one whole factor of x, right? Half a factor of x times it by another half factor of x, and you're going to end up with one factor of x, and that's just x, right? So that's kind of the intuition. This actually agrees with one of the properties of exponents that we learned about earlier, right? B to the m times b to the n equals b to the m plus n. So this is kind of agreeing with that, right? We're seeing that in action again. This you can rewrite as x to the 1/2 plus 1/2, which is x to the 1, which is just x, right? So there's one example of our intuition agreeing with what we would expect. Here's another one. Remember our fundamental intuition of a over b? You can interpret a over b as a times 1 over b, which is the number 1 over b added a times, right? So consider this example, x to the 3/4. Well, we could rewrite 3/4 as 3 times 1/4, and that's 1/4 added 3 times. One, two, three. And then we can again use this property up here to rewrite it as x to the fourth, x to the fourth, x to the fourth. So here this is like saying you have a quarter factor of x, another quarter factor of x, another quarter factor of x. So how many factors of x do you have? Three quarters, right? Three quarters. So again, these exponents are like counting factors, right? How about this? Remember, we could also interpret this as 1/b of a. No, it sounds weird to say it that way. 1/b of a. So, for example, 3/4 or x to the 3/4, we could think of this as 1/4 of 3. We can think of it as x to the fourth three times, and then we get x to the fourth, I'm sorry, yeah, x to the fourth. Oh my gosh, x to the 1/4, x to the 1/4, x to the 1/4. And again, we have this again. So this part here is agreeing with this property of exponents that we worked with earlier. So this idea of exponents counting factors extends naturally to rational numbers and rational exponents. And since multiplication is commutative, we have these two interpretations. So you can write x to the m over n as x to the m to the 1/nth, but you could also write it as x to the 1/nth to the m. So you can do both as long as the numbers are all right, right? So for example, 8 to the 2/3, you can think of it as 8 to the 2 times 1/3, which would be 8 squared to the third, which is 64 to the third, to the 1/3, my gosh, to the 1/3, uh, which is going to be 4. Or we could interpret it as 8 to the 2/3 is equal to 8 to the 1/3 squared, which is 2 squared, which is 4. So this is like a new property of exponents that we've gotten that's going to help us deal with rational exponents. One thing I want to point out, if you look at these two calculations right here, notice that in practice, one interpretation may be more helpful than the other interpretation, just depending on the values involved. So let me like highlight this for a minute here. This you might find difficult to compute, 64 to the 1/3, but this is a lot easier to compute. 8 to the 1/3, that's 2. And then 2 squared is 4. So this is why it's important to have different interpretations. One may be more natural to use, maybe easier to use. It just depends on the context, right? Okay. Now, in the event that x is a negative number, we got to be more careful because if x is a negative number and we're raising it to powers, complex numbers can start to arise. Absolute values may have to appear, and we're going to see that in just a minute here. All right, so recall these properties of exponents. These are ones that we've used a few times, like this one, uh, this one. This is an important one here. B to the negative n is 1 over b to the n. Here, b to the m over b to the n is b to the m minus n. Again, you can think about it as canceling factors, right? If I've got m factors here and n factors here, then some of them may cancel, and I've got this, right? So now we're going to get two more properties of exponents that we've used a couple of times, but now we're going to use them a lot. And so I wanted to specifically state them and show some very specific concrete examples of their use. So hold on a sec. Yeah, weird. My iPad's got a little glitch going on. Okay, so let A, B, and R be real numbers. We're excluding 0 over 0 and division by 0 situations. Then the following hold. A times B to the R equals A to the R, B to the R, and A over B to the R equals A to the R over B to the R. Oh yeah, except in the case when A and B are both negative and R is a rational number with an even denominator. That's when you have to worry about complex numbers and absolute values and so on. These properties are the most intuitive when R is just a natural number. One thing I want to point out here is what this is basically saying is that if you take a product and raise it to an exponent, you can distribute that exponent to each one of those factors. So a times b to an exponent is a to that exponent times b to that exponent. That's really what it's saying. Same with this ratio, this division. You can distribute that r to both of those factors there. Okay, and it'll be equal. You'll still have the same value. Let's look at a couple examples real quick. So here, like think about the fact there's eight, we have eight squared. Eight is equal to two times four, and we can apply that two to the two and the four, and you'll still get 64, just like you would expect with eight squared. Same here, two over three, two squared, three squared, two squared over three squared, which is 4 over 9. And that's the same thing you would get if you did um, 2/3 squared, which would be 2/3 times 2/3, which is 4/9, right? That's the basic idea. So as long as we've got a product or a ratio, then you can distribute those exponents and everything works well. All right. That being said, big word of caution, big word of caution. Beware, beware, red flags, whoop, whoop, whoop. There is no shortcut for a sum or a difference raised to an exponent. Okay? This is one of the hardest habits to break. If you've done this in the past in a previous math class, this is one of the hardest habits to break. If you got a sum or a difference and you're raising that sum or a difference to a power, that's it. There's no special shortcut that says you can distribute that exponent, you could do this and do that. There is not. That doesn't exist. I'm sorry. More specifically, I'll zoom in here. A plus b to the r, it's not a to the r plus b to the r. Sorry. There is no shortcut. There is no shortcut. If you see this raised to a power, you should almost feel your stomach drop a little bit because yeah, that's it, right? There's nothing that's going to make you nothing that's going to make it that simple. That does not, yeah, those don't equal each other. Same thing if it's a difference. If it's a minus b to the r, sorry, it's not a to the r minus b to the r. There's no shortcut. This should also make your stomach drop out a little bit. Yeah, that's just what you got. That's it. Okay. Um, the way that I like to explain it is this. These two results here, these basically say that exponents play well with products and ratios, with products and ratios. Exponents do not play well with sums and differences. No, they don't play well with sums and differences. So as long as you've got a product or a ratio, exponents are great. They work well, they play well together. But if you've got a sum or a difference, they don't play that well together. They really don't. And in fact, in section 5.4, at the end of the next chapter, we're going to learn the binomial theorem, which asserts that a sum or a difference raised to a power actually obeys this formula. Yeah, it's that formula. So you should be like, oh my gosh, what am I looking at? Funny enough, we actually saw this formula in section 3.5 when we were talking about the Weierstrass approximation theorem. That was this being used to give us a polynomial approximation for the absolute value function. Yeah, so we're getting there, but we still have like seven more sections before we get to it. Uh, but again, if you see a plus b raised to a power, it's not this. Sorry. And it's not this. Sorry. It's this. Okay. So beware. And it doesn't matter what R is. R could be a rational number. It could be an irrational number. It could be zero. Like it just, yeah. Just, yeah. Exponents don't play well with sums and differences. They play well with products and ratios because hey, exponents are all about counting factors, right? Factors are parts of a product. So as long as you're talking about products or ratios or divisors, exponents play great, right? Okay, keep that in mind. Now we're going to use these properties of exponents. So we're going to use the properties of exponents to rewrite these expressions so that the bases only appear once, okay? I want you to try at least the first one on your own. Let me explain the goal here. Um, the base here, the bases involved here are x. So I want you to rewrite this expression as x to the something, okay? Just x to the something, okay? So that's the first one I want you to try. Let me throw up the thinker. All right. And then you know what you're going to have to do next. Verbalize it. Verbalize something, say something out loud to give your brain that feedback. And now work it out on your own. Couple of tips. Remember those properties of exponents. Remember exponents are counting factors. Leverage what you know now about fractions and adding fractions and subtracting fractions, and go with your gut in that regard, okay? And we'll do it together in just a minute. Okay. Here we go. So the first one, I've got it written out here. We've got an x to the 1/4 in the denominator. We can rewrite that as x to the negative 1/4. So it's like when we bring it up to the top, it changes the sign of the exponent, right? That's that whole b to the negative n equals 1 over b to the n, that property. We just went in reverse. Okay, now what we've got is we've got a product of three expressions with x in them. So this is x to a power, x to a power, x to a power. That other property of exponents says we can write it as x to the sum of those powers. And now the beautiful part here is we've just got a sum of three fractions. And we talked about that way back in chapter 1, and we've seen how to work with these expressions before. Again, you're kind of like focusing your analysis onto the piece that you're trying to manipulate. So we basically just need to compute this, like so. And if you're able to combine those fractions, then you're able to rewrite something like this as this. So what I did here was I rewrote that in this step. I found a common denominator. In this case, the common denominator is 4. I'm sorry, 4, 12. So I wrote it as 8 over 12 plus 6 over 12 minus 3 over 12, which is going to be 8 plus 6 minus 3 over 12, which is 11 over 12, just like that. So what is this mess here? It's just x to the 11/12. That's it. Yep, that's it. So again, you can leverage what you know, your fundamental intuition about fractions and the stuff we worked on earlier to help you deal with more complicated expressions. That's the cool part. All right, what about part B? So in part B, there were two bases. So in this case, our final expression should have an x factor and a y factor, or x expression and a y expression. Everything else is all the same. Remember, if you get overwhelmed with these kinds of things, it's okay. Just pause for a minute, take a deep breath, and just follow your nose. Nobody expects you to be able to jump from this to that, okay? You're not expected to do that. Nobody is requiring that of you. Just write out some steps, carefully organize your work as a chain of true equalities. It will help you avoid mistakes. So don't like write something here and then here and then here and then here. Try to write it as a chain of equalities respecting the equal sign. This has to be equal to this, which has to be equal to this, which has to be equal to this, which has to be equal to this. Okay, let's do it together right now. Um, okay, so here I've got some stuff raised to a power, and that new property of exponents that we learned says we can distribute those to each one of those factors. So let's do it. Let's see, x to the 1/4, y to the 1/4, right there. Maybe I can zoom in a little bit. There you go. X to the 1/4, y to the 1/4. Here, we get x to the 1/2 times 2. I'm sorry, 1/2 times 2, and then 1/2 times 2 gives us this. All right. Uh, here, oh, and then down here, 3/4, distribute it, multiply it by 2. You get 6/4. 3/4 to the y. There we go. Given to the y, I should say. All right, now we can do a couple of things. We've got this expression in the denominator. We can bring it up to the numerator. We just have to change the sign of those exponents, and that's what I did right here. Bringing it up changes the sign. Pushing it down changes the sign. These remain the same. 2 to the 2, I'm sorry, 2 over 2 is 1, so we can just write this like so. Now we've got a whole bunch of x's and y's all on the same level, all being multiplied. It's great when they're all being multiplied. Exponents love working with products, right? They play well with products. Um, Now we're going to combine all of these expressions that involve x and all these expressions that involve y. Here's one, here's one, here's one. So we're going to write it as x to the all of that. And here's one with y and y and y. So we're going to write it as y to the all of that. And now we're back to where we were in the previous problem, right? We just have some fractions that we need to add up. We've got practice with that. We'll get more practice here. Simplify this sum and difference, simplify that sum and difference. You get -1/4, you get 1/2, and boom, that's it. That's it. So long story short here, this big mess that you see up here is really just x to the -1/4 and y to the 1/2. When you simplify everything down, that's what you get. Cool stuff. Okay. Now we got to talk about factoring expressions with rational exponents. One of the more important skills in calculus that you're really going to need is the ability to factor expressions that have rational exponents. Why? Again, like, why is that important? Why do I need to learn this? Well, if you remember, like we saw in chapter 3, factoring expressions lets us analyze the local behavior of functions that have those expressions in them, right? So you're going to be exploring more functions that have rational exponents in Calc 1, and being able to work with those rational exponents and factor them is going to let you perform a local analysis of those functions. It'll help you find things like zeros or asymptotes or cusps. You know, cusps are those little like points. That's what you're going to do in Calc 1. So you want to get comfortable factoring with rational exponents. And to make that process more intuitive and more straightforward, just remember that exponents are counting factors. Appeal to counting, appeal to intuition for fractions, appeal to remainders, as we did above and as we were doing in chapter 3. Okay, you can use all of that to make this stuff more intuitive and easier to understand and more motivated, right? Okay, so here's an example. We're going to factor this, okay? Factor this. And I think I'll ask you to try this one on your own first. I want you to think about how you could factor this expression, okay? Think about it for a minute. Okay, now verbalize something. Say something out loud about anything. Maybe what's a common factor that you see? Okay, and now try to work it out on your own. My tips are: what is a common factor? And remember that exponents are counting factors. All right, here we go. So when I look at this expression, first thing I notice is there's two terms. Okay, there's this term here, and there's this term here. So I need to look for common factors of these two terms. Let me highlight them actually. There's this one, and there's this one. So I need to look for common factors of both of those things. And what I notice here is this factor, I'm sorry, this term has a factor of 1/3. This term has a factor of, I'm sorry, x to the 1/3 and x to the 4/3. So they're sharing a common factor of x to the 1/3. We can factor that common factor out and see what's left. Here we go. Common factor of 1/3. So I'm going to factor 1/3 out of this and that. And then when I factor a 1x to the 1/3 out of this, I'm left with 2x plus 1. When I factor an x to the 1/3 out of this, I'm just going to count. If I had 4/3 factors and I took away 1/3, how many factors do I have left? 3/3, right? I had 4/3. I took out 1/3. How many do I have left? I have 3/3. There it is. Okay. And the best part is, let's say you don't feel confident, which is totally fine. Maybe you're like, did I do that right? You can check, just redistribute it back to see if you get what you had in the beginning, right? So here is x to the 1/3. If I multiply that by x to the 3/3, I'm gonna get x to the 1/3, x to the 3/3, which is x to the 1/3 plus 3/3, which is x to the 4/3, which is what I started with. Awesome. I'm good. I did it right. Okay. Now let's continue. Let's proceed from there. I factored out the 1/3, x to the 1/3. I'm left with 3/3. Now, 3 over 3 is just 1, so I'm just going to write it as x to the 1. And now I can simplify what's in the middle here. I've got a 2x plus 1. I've got a 2x. I can combine like terms and get 4x plus 1, and boom. We just factored this into this expression here. There it is. Cool stuff. Okay, let's try another one, okay? And I want you to try this on your own before we go through it together. Same thing. I want you to factor this expression, and we'll do it together in a minute. So let me throw up the sequence here. Think about it for a minute. Okay, now say something out loud, verbalize something to help you help jog your brain a little bit. All right, now try to work it out, factor it, simplify it, and we'll do it together. Okay, here we go. Let's do it together. Same thing as we did before. I see two terms here. I've got this term here. I've got this term here. Let's see if I can find any common factors. Looks like there's some common factors. I mean, there's a common factor of 6. Then there's a common factor of 4x minus 3 to the 1/2. Look, this one's got 3/2 factors. This one's got half of a factor. So they each have a half of a factor in common. You could even think of 3/2 as 1.5. If I've got 1.5 and I've got half, the common amount is a half, right? So we can pull out half of a factor of 4x minus 3 from each of these terms. Let's do it. Here we go. Um, and the 6, of course. Okay, so I'm factoring out this common factor, and then what's left? All right, well, again, here, sorry, maybe I'll just go down here, right down here. If I had 1.5 factors and I take out half of a factor, how many factors do I have left? One, right? I have one. 2 over 2, that's one. Um, and then here, if I have half a factor and I take out half a factor, how many do I have left? I've got 0, right? Well, anything to the 0 is 1. So that's it. You're left with just 1. Anything to the 0 is 1. Again, 2 over 2 is equal to 1. So we can simplify that. 2 over 2 is 1. And then here in the parentheses, I'm left with 4x minus 2, right? Because I had a negative 3 plus 1 is minus 2. Now what I notice is that I can actually factor out a little bit more. Now that I've gone through this simplification, look, those two terms have a common factor of 2. So I can factor out a 2. Actually, I'll put it all the way at the front. Factor out a 2. 2 times 6 is 12. And voila, there it is, fully factored. Cool stuff. So you see, it's not really that hard. You just want to remember that these are kind of counting factors, right? And just think about adding and subtracting and removing and putting in, and that'll help guide you when you're on these types of problems. All right. Now, we're going to do this one a little bit differently. We're going to factor this one in two different ways. And maybe maybe a little revealing here. I always put this question on one of my Calc 1 exams, all right? And on that exam, you have to do a full graphical analysis of this function and then graph it. So pretend it was like what we did in section 3.9, but for this function and even more information that you had to get, right? So the very, very first step is you have to factor this. That's step number 1 of that problem. So we're going to factor it in two different ways. Hold on a sec. Okay, here's what we're going to do. I want you to try this on your own, but I want you to start by factoring out a factor of x to the 2/3 from both of these terms, okay? That's what I want you to try on your own. So ponder it for a minute. Okay, say something out loud. Maybe what'll be left when you factor out x to the 2/3. And now work it out. Try to write it on your own. Factor out x to the 2/3, and we will do it together in a moment. Okay. All right, here we go. So, um, again, I'm just going to appeal to counting the whole time, right? So if I'm going to factor out x to the 2/3, this has 2/3 x's. I'm taking out 2/3 x's, so I'm left with 1. I took away all of them. I'm left with 0 x's. Anything to the 0 is 1. Now here, look at this one. I've got -1/3, and I'm taking away 2/3. So that's -1/3 minus 2/3. -1/3 minus 2/3 is -3/3. So that's -1. And there it is. 5 times x to the -1. Or we could write it like this, just like so. Okay, let me run through that one more time. Um, I have -1/3 factors of x, and I want to take out 2/3 factors of x. So that's -1/3 minus 2/3, just like that. -1/3 minus 2/3 is -3/3, which is -1, just like so. And then we can write it like this at the end just to make it look a little prettier in that respect. Um, so yeah, and again, remember, if you're worried that you did it wrong, right? You don't feel confident, like, did I factor that out right? Remember, you can always go in reverse. Go in reverse. If I take x to the 2/3 and I multiply it by x to the -1, let me write this out here. X to the 2/3 times x to the -1, that's x to the 2/3 minus 1, which is x to the -1/3, which is what we started with. So we're good, right? That's how you can check. You don't if you don't feel confident in knowing that you can check. Okay, you can always just go and check it. All right, and I encourage you to do that. Just check it. If you're doing this problem on a test, or maybe in like my Calc 1 class, right? If you're not if you're worried that you could have done it wrong, just check. Just check it, and it will save you all the points. Right? It'll save you all the points on the test. So that's one way to factor it. And again, maybe some motivation here. The reason we do that is because now we have information about this function. I know the zeros of this function, and I actually know something's going on here when x is equal to 0. Yeah, x is in the denominator there. What's going on there? I'll let you discover that next semester. Okay. All right. Oh, sorry. Okay. Now, that being said, the next thing I want you to try is I want you to try to factor out x to the -1/3 instead. So now factor out x to the -1/3 instead. Okay, so go back all the way back to the original, and I want you to factor out x to the -1/3 and see what you get. Okay. Um, all right, I'll just do this. Okay, think about it and then work it out, and we'll do it together. All right. Okay, let's do it. So, same kind of reasoning. We're going to appeal to counting, appeal to working with fractions. So, if I'm factoring out x to the -1/3, well, I've got x to the -1/3 here. So when I take that out, I'm taking all of that out, and I'm just left with this coefficient, -5. Now here, I've got 2/3 factors of x, and I'm taking away -1/3. So that's 2/3 minus -1/3. 2/3 minus -1/3. Okay, well, 2/3 minus -1/3 is 2/3 plus 1/3, which is 3/3, which is 1. So now we've factored it again, right? Factored it again here. X to the 3/3 is x to the 1, and now we've factored it again. Again, some motivation. Something's going on at x equals 5 too. Yeah, something's happening at x equals 5. When x equals 5, you get 0. You get a 0, right? Preparing you for Calc 1. Um, Again, appeal to counting. All I'm really doing here is I'm treating these numbers as counting numbers, and I'm just running through it intuitively, right? If I've got 2/3 and I want to take away -1/3, I'm subtracting -1/3. Remember, our fundamental intuition of subtraction is a taking from, right? A taking from, or a removing, or a taking out. That's really all I'm doing here. Okay, now want to have a brief discussion about irrational exponents, okay? We've kind of avoided them here, but it turns out that we can extend the properties above to irrational values as well. But the mathematics required to validate that and put it on a sound logical foundation is subtle. And this is something that you will do when you get into calculus 2. All right, you're going to do that rigorously in calculus 2. You're going to prove that you actually are allowed to do all this stuff, even when the exponents are irrational numbers. Okay, for our purposes, we're just going to assume that we're allowed to do that, and we're going to save those subtle proofs that require calculus for when you get into calculus. Okay. Now, what we're really saying here is that the operation of exponentiation is a continuous operation on R. And what that means is really any real number can be an exponent. And why we're allowed to do that, well, you'll prove it in Calc 2. Okay. So now let's talk about radicals. All right. So we spent all this time so far talking about rational exponents. Now let's talk about radicals. We've seen them a couple of times already, but let's put them on a little bit more of a logical foundation. Okay. So we're going to suppose A and B are greater than or equal to 0, and we're going to suppose that n is not equal to 0. Then the principal nth root of A is denoted by n radical A, and we define it as the positive solution to this equation. So in essence, if we wanted to solve this equation for b, we would take the nth root of both sides and get that b is equal to the nth root of a. So very literally going like nth, like so. All right. So this is what we call the nth root of a. The symbol here is called a radical. The number n is called the index, and the expression inside the radical is called the radicand. We've seen that before, like when we were talking about the quadratic formula, right? The radicand is just the stuff inside the radical symbol. Okay, that's it. Excuse me, excuse me. Um, so what's nice about this definition is that it lets us use this corollary, and this corollary lets us connect rational exponents to radicals. So here's the punchline, I suppose. If a is a non-negative real number and n is a non-zero real number, then the nth root of a is a to the 1 over n. So this is the connection between radicals and rational exponents, okay? Whatever that index is, you're going to have a to the 1 over n. Obviously, n can't be 0, all right? So for example, what is the cube root of 125? It's 125 to the power of 1/3. And 125 to the 1/3 is equal to 5. That's it. So wait, do I say this on the next one? Oh no, proof. Okay. Proof of it first. So if a is equal to b to the n, then if we exponentiate both sides to a power of 1 over n, we get this, right? Starting here, raise, oops, raise both to a 1 over n, 1 over n. We get a to the 1 over n equals b to the n, to the 1 over n. Properties of exponents say that we can multiply those two exponents. We get n over n. N over n is 1. B to the 1 is b. And b is the nth root of a by definition. So again, we're showing that this is equal to that radical right there. Okay? So here is the utility of this. Again, like why do we care about this? What's the purpose? This identity can really simplify our lives and make things way easier because it asserts that rather than work with radicals, you could instead work with rational exponents. And frankly, most of the time, it's going to be more efficient to work with rational exponents than it will be to work with radicals. I mean that mathematically speaking. I also just mean it symbolically speaking, because when you got a lot of radicals flying around, especially when the indices are different numbers, it can get visibly overwhelming, like visual clutter, and it like affects your brain where you're like, oh my gosh, I feel like I can't see anything. Like I'm staring into a mess of twigs and branches that aren't, I can't even understand where the trees are. So the good news here is if you see a radical, you can just write it as an expression with a rational exponent, and that will make your life way easier. In calculus, it's going to be like a standard step. The reason is because there's a really important technique or really important rule in calculus called the power rule, and it basically allows you to compute the derivative of things like this. How do you do it? You write them as a rational exponent, and then you use the power rule. There's also one for antiderivatives, and you'll talk about that in Calc 1, where if you want to find the antiderivative of something that looks like this, you write it as this, and then you use the power rule. So it's an important transition between those two. That being said, not trying to put down radicals so much. Sometimes using a radical can be more concise or more suggestive. Sometimes it's easier just to say radical 2 than 2 to the 1/2. Kind of depends on the context, right? Okay, so here are some properties of radicals. We've used a few of these already, but there's a couple new ones here that I want to talk about for a sec. Let's just stick to non-negative real numbers, and we're going to let m and n be integers with n not equal to 0. Then the following properties hold. The nth root of ab equals the nth root of a times the nth root of b. The nth root of a over b is the nth root of a over the nth root of b. And then this, we can basically move things around a little bit. So the nth root of a to the m is equal to the nth root of a to the m, kind of reassociating there. I'm going to hold off on these for just a minute here. I want to focus on these for a little bit more. Remember that we can write radicals as rational exponents, okay? So this here is really just the standard property of exponents that we saw earlier, because you can think of this as, I'll write it down here for some space. A times b to the 1 over n is a to the 1 over n, b to the 1 over n. That's what this is saying. Oops, there you go. That's what this is saying. And again, exponents play great with products and ratios. Exponents love to play with products and ratios. They work really nicely because they're counting factors, essentially, right? That's also why this one works. So here we've got a over b to the 1 over n, and that 1 over n is getting passed to each one of those factors right there. Same kind of thing. This one also follows from just writing this as a rational exponent instead. All of these follow from just writing it as a rational exponent. That's why rational exponents are so nice. All right. Now, these I want to pay some special attention to, 4 and 5, because there's a subtlety there. There's a subtle point. First, let's look at number 5 first. Maybe I should even switch the order of these in the future. Um, the nth root of a to the n is a, but only when n is odd. Okay, so what I'm really saying is that the nth root and the power n are canceling each other to give just a, but only when n is odd. Only when n is odd. There's a catch when n is even. If n is even, then the nth root of a to the n is actually the absolute value of a. So they're not just canceling out. That's why you got to be careful. Nth root of a to the n, they'll cancel as long as n is an even number, an odd number. But if n is an even number, they won't just cancel. You're actually going to get absolute value. In fact, this right here is an equivalent definition of absolute value. And let me show you why this is the case. Think about this. Think about, okay, if we do the number 2 to the 4th, okay, and then we take the 4th root of that, they're going to cancel out, right? So this will kind of cancel with that, and you're left with 2. Believable, okay? But now watch what happens when I do this. Maybe I'll do negative 2 to the 4th, and then do the 4th root. Okay, well, what's negative 2 to the 4th? Negative 2 to the 4th is 16, and the 4th root of 16 is 2. But negative 2 is not equal to 2. Right? So here we had negative 2 to start with. Now we have positive 2. Negative 2 is not equal to positive 2. So when it was a positive number, when I did positive 2, I got positive 2. But when I did negative 2, I got positive 2. So what it's doing is it's taking positive numbers and just spitting them out again, but it's taking negative numbers and taking their opposite to make them positive. Does that sound familiar? I hope it does, because that is literally the absolute value. That's the absolute value function. So this is an equivalent way of writing absolute value. You just do an even index radical of a to that even index, and that's the absolute value. Okay, interesting stuff. So be careful. They don't just cancel. It depends on the evenness or oddness of that index. Okay, let's do some examples. And these, I'll just walk through these ones. So here, square root of 32, we can simplify this radical by pulling out perfect squares. That's basically the idea. So 32 is 16 times 2. Properties of radicals let us rewrite it like this. The square root of 16 is 4. Square root of 2 is square root of 2. So then we get 4 times the square root of 2, just like so. Cube root of 16, we can pull out perfect cubes. So 16 is 8 times 2. Properties of radicals say we can rewrite this as cube root 8 times cube root 2. Cube root of 8 is equal to 2. And then we're left with 2 times cube root of 2. What about this one? Okay, so here, we're not going to be able to pull out everything, but we can split things up and try to look for perfect cubes again, all right? So negative 8 times 2, x cubed, x, uh, negative 8x cubed, and 2x. This, yeah, and then we're going to split it across this and this. Split, split. Um, we'll be able to cancel these, and then cube root of negative 8 is negative 2. So this all kind of comes out like that. And then you're left with cube root of 2x. This is the thing that is not a perfect cube, so it kind of stays in the radical. All right. Let's do one that's a little bit more complicated. And then I'm going to give you some intuition to help you do this kind of stuff in about 2 slides, okay? Here we're doing the fourth root of 16x to the fourth over 81. And what we're doing is we're trying to look for perfect fourths. Now, the caveat here is this is even. This is even, and we don't know if x is always positive, right? So absolute value is going to get involved here, because if we want to simplify that, it's not just going to be x, it's going to be absolute value of x. Let's walk through it. 16 is 2 to the fourth. 81 is 3 to the fourth. Properties of exponents will let us rewrite it like so. 2x over 3 to the fourth. Now, we would like to say that those things will just cancel, but they won't exactly cancel. They'll leave us with absolute value of 2x over 3. Okay, that's what it will do, because this index is even, and x could be positive or negative, we don't know, or 0, we don't know. Absolute value of 2/3, using properties of absolute value, we're just going to get 2/3. So this simplifies to that. So this whole big mess can just be written as 2/3 absolute value x. Much cleaner, I think. All right. Down here shows again why this kind of simplification can make things look a lot more elegant or a lot prettier. Square root of 12, we can pull out a perfect square from that. There's a perfect square of 4 as a factor of 12. So we can write 12 as root 4 times 3. Then we can split this up. So negative 8 times square root of 4 times 3 is negative 8 times square root of 4 times square root of 3. Square root of 4 is 2. 2 times negative 8 is negative 16. And now what we have is we have like terms. We have common terms here. We've got negative 16 root 3's and 1 root 3. And so that simplifies as negative 15 root 3's. There it is, right like that. Okay? Okay. Now, this is all pretty technical, and you don't need to write out all of these steps if you can think of an easier way to do it. If you know how to do it more easily, you can do that. Don't feel compelled to have to do it this way. But let me give you some tips and some intuition for how to do that. So so the nth root of x can be written as x to the 1 over n, we can use properties of exponents. We can appeal to our knowledge of the division algorithm and remainders, and we can leverage mixed numerals to simplify our simplification. That might sound kind of funny, but you're going to be surprised at just how much that division algorithm and working with fractions can make things way easier. Just being comfortable with remainders and whole parts and fractional parts, that makes things really easy in a lot of different mathematical contexts. So if we write a rational exponent as a mixed numeral, then we can see how many wholes there are, how many whole factors, and what the fractional part is, just like we saw in section 1.2 and 3.9, all that stuff. And what this allows us to do is pull out the whole factors of a number from the radical and leave the partial factors under the radical sign. Okay, I'll do one example and explain it, and then I'll give you a couple other examples to try on your own. So here's one example. First, for ease, we're going to assume A, B, and C are non-negative, and I'm going to zoom in on this. Watch this process, okay? This process is just going to be it's just really beautiful and elegant. Rewrite this radical as a rational exponent, right? So big mess inside. Don't worry about it. We're going to clean it up right now. This becomes to the 1/5. Properties of exponents let us distribute this to each one of those factors: 17/5, 8/5, 9/5. Now, what we're going to do is we're going to rewrite each one of these rational numbers as a mixed numeral. Okay, so how many times does 5 go into 17? 3 times with a remainder of 2. So it's 3 2/5. How many times does 8 go into 5? Once with a remainder of 4. I'm sorry, remainder of 3. So that's 1 3/5. How many times does 5 fit inside of 9? Once with a remainder of 4. So that's 1 4/5. Okay, now what I want you to notice here is we have 3 whole factors of A, 1 whole factor of B, 1 whole factor of C, and then we have some fractional parts, some fractional factors, right? So I'm going to mush all of the whole factors together, A cubed, B, C, and I'm going to put all of the fractional factors together, A to the 2/5, B to the 3/5, and C to the 4/5. There it is. Now, again, using properties of exponents, we can just rewrite this as A squared B cubed C to the 4th to the 1/5 to get that radical. And that's it. That's it. Maybe more, what word am I thinking of? Maybe more expediently, all we really had to do was take these numbers, divide them by 5, pull out the whole parts, and then leave the remainder parts in there. So again, oh, wait, I say that on the next slide, don't I? Yeah, there we go. That's the next slide. Okay, so just jumping from the very beginning to the very end here. Here we just divided each one of these exponents by 5 and then left the remainders in. Okay, so again, 17 divided by 5, that's 3. So I'm going to have 3 whole factors of A that can come out. 8 divided by 5 is 1 plus a remainder. I have 1 whole factor of B that comes out. Same with C. I have 1 whole factor of C that comes out. And then what's left? The remainders. The remainder when you divide 17 by 5 is 2. When you divide 8 by 5, it's 3. When you divide 9 by 5, it's 4. And you just leave those partial factors in there. That's the idea, because when they're raised to the 1/5, that's a partial factor, not a whole factor. Um, so that's it. Like, that's it. These things are, fun to simplify once you realize you're just using division and you're just rewriting it as a mixed numeral. That's really all it is, okay? Now, if sum of A, B, or C could be negative, then you just got to be a little bit careful and use absolute values if the index is even. That's it. So if the index is even, when you're pulling things out, you're going to have absolute values instead of just not, okay? Now you try. So here we go. I'm going to give you these two radical expressions, and I want you to try to simplify them by factoring out or pulling out as much as you can, okay? So ponder it for a minute. Now, verbalize something. Say something out loud, maybe what you'll do first or what you notice first, right? And now work them out, and we will do it together in a moment. All right, here we go. So, yeah, here we go. Let me zoom in a little bit. In fact, let me do this. Hold on. There we go. Zoom in a little bit. Okay. So what I would do when I see this is I'm just doing division in my head and asking how many times this number goes into that number and then leaving the rest. Okay. So how many times does 3 go into 26? Let's see. 3 times 8 is 24. So that should be 8. So I've got 8 whole factors of a. Okay. And then what's left over is the remainder. So a squared. Let me write this a little more cleanly. 3a squared, right? 3 times 8 is 24, and there's 2 left. Okay, how many times does 3 go into 15? 5 times. So I'm going to have b to the fifth, and there's no remainder. There's no remainder, so that would be b to the 0, but b to the 0 is just 1, so I'm not even going to rewrite it. There's no b's left over. I took all the b's out. Let's see, -7. How many times does 3 go into -7? Well, that's going to be what? 2 times? But it's negative, so we're going to have c to the -2. And then what's the remainder? C to the -1. -1. Let me check. See, this is one of those times where I'm like, wait, do I believe it? Do I trust myself? Don't need to. I can check, right? See, this is c to the -2. -2 times 3 is -6. -6 plus -1 is -7. I'm good. Nice to check. I did it. Okay, now same thing here. Let's do the next one. Ooh, okay. The index is even. So if you don't see a number here, that means the number is 2. We always assume that's the square root of those numbers, but it's even, and A, B, or C could be negative, so we got to be careful. We got to use absolute values. Okay, so how many times does 2 go into 6? 3 times. So we're going to have 3 factors of absolute value of A, right? How many times does, oh, and then there's no A's left, A to the 0, right? Hold on, put a 2 there. Okay, how many times does 2 go into 5? 2 times with a remainder of 1. So we'll have b squared, we're gonna have a b left over. And then how many times does 2 go into 9? 2 times 4 is 8, so 4 times. 2 times 4, and then we're gonna have 1c left over, and that's it. Let's see, did I get it? I hope so. Yes, got it. Okay, nice. All good. All right. So that's it for that part. The last thing we got to talk about is rationalizing parts of an expression. Okay. Um, yeah, this actually will go pretty quick now that I think about it. Rationalizing parts of an expression. So, if there are irrational terms in an expression, sometimes it's helpful or revealing to rationalize that part of the expression. Rationalizing just means converting an irrational part of an expression into a rational part by shifting the irrational part somewhere else, okay? Um, Really, that's all it is. We're kind of moving the irrationality somewhere else in the expression. How do we do that? Well, we're just going to multiply by a clever one again. There's that technique popping up. Multiplying by a clever one, adding a clever zero, two most important techniques in math over and over and over again. We're going to multiply by a clever one, and what'll happen is that will convert the irrational part into a rational expression and move the irrational part or move the irrational stuff somewhere else in the expression. One important note I want to make here, this does not remove the irrationality of a number. Okay, so rationalizing an expression or part of an expression does not mean that it becomes rational all of a sudden. The irrationality is still there. It's just been moved around somewhere by some massage. It's like moving the kinks somewhere else. It's not getting rid of the kinks, it's moving the kinks somewhere else. That's all. Okay. Um, so when expressions with fractions are involved, we often say rationalize the numerator or rationalize the denominator, for example. Okay. So let's try this one. I'm going to do this one and I'll let you do the next one. We want to rationalize the denominator of 1 over root 3. So what I'm really saying is I want to massage this expression into one that does not have an irrational number in the denominator, okay? Rationalize the denominator. So what are we going to do? We're going to multiply by a clever one. The clever one in this case is the square root of 3 divided by itself, okay? Square root of 3 divided by square root of 3, that's 1. That way, when we multiply these two factors in the denominator, radical through square root 3 times square root 3, that's just going to be 3 because that's square root of 3 squared, which is just 3. And that's it. Now, the denominator has been rationalized, right? Rationalized. So the denominator is a rational number, but now the numerator is the numerator is an irrational number. So we just moved the irrational stuff up. That's pretty much it. But how did we do it? We had to do it in a valid way. We can't just like move it willy-nilly. We can't just say, oh, just put that in the top and we're done. That's not a valid manipulation, right? Remember, with expressions, you can basically add 0, multiply by 1, factor it, complete the square, something like that. So you got to do it in a valid way. You can't just like put it up there because you wanna. You've got to do it by multiplying by a clever one. Okay? Okay, now I want you to try this one on your own. So I want you to try to rationalize the numerator of this expression. Okay? So think about it for a sec. Right? Now, give yourself some verbal feedback. What are you going to do first, maybe? All right. Now work it out on your own, and then we'll do it together. Maybe I'll give you one little hint. Um, your clever one is going to be a little different than the clever one we saw in the previous example. Okay, here we go. All right, so we want to rationalize the numerator, and we're going to multiply by a clever one. The catch with this example is this is a cube root, not a square root. So if we want to get rid of that irrationality in the top, we're going to have to multiply by a couple factors of cube root of 4, not just one. More specifically, we're going to have to multiply by this, okay? In fact, you're going to have to multiply by uh, you're going to have to multiply by enough factors to get the index number of factors wherever you need it to be. So here, when we multiply by cube root of 4 over itself twice, in the numerator, you're going to get 3 factors of cube root of 4. And when you do that, you're going to get that simplification. So here's a situation where you needed 2 factors of cube root of 4. So that way you end up with 3 of them in the numerator, and then that will simplify to just 4. Now the denominator is a big mess. You've got this down here in the denominator. We can simplify it a little bit. We can massage it a tiny bit. Cube root of 4 is the same as cube root of 4 squared is the same as cube root of 16, using that property of exponents we saw. Then cube root of 16, we can simplify that. It's got a perfect cube in it. That's a 8. Cube root of 8 is 2, so we can pull that out. And then we're left with this. And then we can do a little more simplification. 28 divided by 2 gives us 14, and boom, there we are. So now look what we did. The original expression had an irrational numerator. Now it has a rational numerator, but an irrational denominator. So we moved the irrational part to the bottom in a valid way. All right. Okay, next we're going to do one more. This is one more example. You'll get lots of practice with these on the homework too. We're going to rationalize the denominator of this expression. And this one I want to do just to kind of show you how to do it. Because the technique we're going to leverage is a little bit different. We are still going to multiply by a clever one, but the clever one we choose has a different structure than the previous two examples. So here we go. In cases like these, we're going to leverage a difference of squares. So just a reminder, hopefully you've got this memorized. A difference of squares looks like this. So a minus b times a plus b expands to a squared minus b squared. Now, there's a really clever trick that we can use in math. We can pretty much rewrite any difference as a difference of squares as long as those numbers are positive or zero. So if we assume that a and b are zero, then a minus b can be written as square root of a squared minus square root of b squared. But then this is a difference of squares, which factors like so. Why is this handy? Why is this handy? Because we can basically take this product and write it as a minus b. So what we're really doing here is we're going to take this denominator, which looks kind of like this, and we're going to multiply it by its conjugate. Its conjugate. Remember that? That term was one we learned back in section 3.6 when we were talking about complex numbers. And if you remember, the conjugate was just changing the sign in between those two terms. Same thing here. We're going to take this and we're going to multiply it by the conjugate of the denominator divided by itself. Here we go. This is it. So what is the conjugate of root 3 minus 3 root 2? Root 3 plus 3 root 2. Here's our clever one. Now we're going to simplify. The denominator is now a difference of squares. The numerator, big mess. Don't worry about that, big mess. We're just moving the mess around, all right? So the numerator, we're going to take root 2, distribute it to there, distribute it to there. There we go. Denominator, we're writing as a difference of squares. Now we can simplify. Square root 2 times square root 2 is square root 6. Square root 3 is square root 6. Square root 2 squared is 2. To get 3 times 2. In the denominator, root 3 squared is 3. 3 times square root 2 squared is 9 times square root of 2, right? We're just distributing those exponents or that exponent there. Now we simplify some more. 3 times 2 is 6. 3 minus 18 is negative 15. And voila, there we are. So now notice the denominator is rational. We rationalized the denominator. All right. And on that note, let's play. All right. Okay. So this is the beginning of chapter 4. We just learned a ton about exponents and radicals. They're really, really going to help us out in the future. They're going to help you out a ton in Calc 1. The next section is all about exponential functions. So I'll leave you at that. Thank you all again for watching, and I will see you next time. Have a good one, everybody.